Okay, so good evening, everyone. So welcome to the Special Functions and Number Theory seminar. Today we have a speaker from the US, Rishabh Sharma from Penn State. He'll be talking on modular symmetries for partition and over partition statistics. Over to you, Rishabh.
Thank you, Atul sir, and thank you to all the organizers for inviting me to speak here. I have heard of this seminar. I have been here not that many times, maybe twice before. Once Professor Garvan, my PhD advisor, gave a talk here. I was either in that one or the one given by Jeremy Lovejoy on a joint work. And I'm glad to be presenting here today. And thank you everyone for coming to my talk. This is a work which involves some joint work with my PhD advisor Frank Garvin, and it has some of it. A part of it is also something that I did during my PhD. So when I say partition and over partition statistics, I mean rank and crank functions. So some background and motivation. I don't think I need to talk about this slide, but just for the sake of it, I'm pretty sure people here are from the theory of partitions. People work mostly in the theory of partitions, so I don't think I need to explain these things, but maybe I'll start right here that this is the finite Pokemon symbol, and the infinite version of that is obtained by letting n go to infinity, and the product of those products is denoted by this. And a Q series, also called in literature as an Eulerian series or basic hypergeometric series or Q hypergeometric series, is constructed from these Q Pokemon symbols. And generically, they take the following form. I've had a debate with Alexander Berkovich at UF who says that maybe this does not encapsulate all the types of Q series that we have, but I'm still going with it. And depending on whether you can replace AIs and BIs by whatever you want to get the Q series that you want.
Did he mean that you have to put the -1 to the n q to the n plus 1 by 2 to the power r in there?
Yes, stuff like that here. Moving on, here are the functions or building blocks that I'll be using in my talk. The Dedekind eta function, modular form of weight half, the generalized eta function defined by the following, and something that I'm calling Biagioli theta functions, so these functions, I'm calling them Biagioli theta functions because I have seen them first defined by Biagioli, I guess, in one of his papers, where he talks about their transformations and modularity. And these Biagioli theta functions, they can be written in terms of the generalized eta function and vice versa. Further, for a vector n, which is a p plus 1 over 2 tuple, I'm defining the function jz to be a product of those Biagioli theta functions with these elements of n as its exponents, and k's, k ranging from 1 to p minus 1 over 2, along with this eta multiplier out of the front, whose exponent is the first element of this tuple. And if fz is a meromorphic function on the upper half plane and k is an integer, then we define the slash operator by the following, which is pretty well known. That takes me to the celebrated concept of Ramanujan, which I think almost everyone has seen. Any talk in the theory of partitions and Q series, I think, begins with these congruences found by Ramanujan and also proved by him in 1919, where he states that the partitions of 5n plus 4, 7n plus 5, and 11n plus 6 are divisible by 5, 7, and 11 respectively. And although in his paper, Ramanujan gave a proof of these congruences, a combinatorial interpretation of these congruences was missing until Freeman Dyson came into the picture in 1944 as an undergrad at Cambridge University. He wrote a paper in their undergraduate journal, Eureka, where he defined something that is called Dyson's rank of a partition, which is the largest part minus the number of parts of the partition. Here is an example. For the partitions, the ranks are being calculated for the partitions of the number 4. So after calculating the rank and reducing them modulo 5, we can see that there is a partition of the number 4 in each residue that has rank in each residue class modulo 5. And this is not a coincidence. This is in fact the Dyson's rank conjecture, which states that if nRTN denotes the number of partitions of n with rank congruent to R modulo T, once again rank is the largest part minus the number of parts, then we have the following. So as to say, the rank statistic divides the partitions of 5n plus 4 into 5 equinumerous classes and 7n plus 5 into 7 equinumerous classes, thus providing a partial combinatorial interpretation of the Ramanujan congruences modulo 5 and 7. These two conjectures were proved by Atkin and Sunderton-Dyer in 1953, and they explain the 5 and 7 congruences of Ramanujan, but they fail in the model 11 case. In the very same paper that appeared in Eureka, Dyson also prophesized the existence of another statistic that he is calling the crank, which, as he says, it is an arithmetical coefficient or a statistic similar to but more recondite than the rank. I shall call this hypothetical coefficient the crank of a partition, which would eventually explain the mod 11 congruence of partition congruence of Ramanujan in the same way. And it was not until 44 years later, I believe, when George Andrews and Frank Garvin found the crank of a partition. They define it as the largest part if there are no ones in the partition. Otherwise, it is the number of parts larger than the number of ones minus the number of ones. And it not only explains the mod 11 congruence of Ramanujan, but it also divides the partitions of 5n plus 4 and 7n plus 5 and 11 plus 6 into 5, 7, and 11 equinumerous classes. That takes me to the 1987 Ramanujan Centenary Conference at UIUC, where Freeman Dyson gave a lecture and he called for the search of a a coherent group theoretical structure that would somehow incorporate the mock theta functions of Ramanujan into the realm of modular forms. And as he says, this remains a challenge for the future. Since this talk is just for an hour, I'm not going to focus on mock theta functions. They are also as legendary as Ramanujan's partition congruences and these rank and crank statistics, and they are related to rank and crank statistics, which is what I'm going to explain now. If nmn denotes the number of partitions of n with rank m, then many of Ramanujan's mock theta functions can be written in terms of the two-variable rank-generating function rzq, where we replace the variable z by a primitive pth root of unity zeta p. Here is an example. The following mock theta function of Ramanujan is equal to r minus 1q, where we replace z by minus 1. The first big breakthrough in Dyson's prophecy came in 2002 when Sanders Zwegers, in his PhD thesis, showed how the mock theta functions occur as the holomorphic part of certain real analytic modular forms. Brinkman and Ono, building on Zwegers' work in 2008, I believe, they found that the rank-generating function, once again z replaced by the primitive pth root of into zeta p, is the holomorphic part of a weak mass form of weight half on the large congruent subgroup gamma 1 576 p to the power 4. Brinkman, Ono, and Rhodes used this result to prove that the rank sum modulo p is a weakly holomorphic modular form of weight half on gamma 1 576 p to the power 6. And many years later, Garvin, in a paper that appeared in the Transactions, he showed that the adjustment of the rank generating function, which is to say the same rank generating function with some correction factors, which creates this this function Rp times the eta product, eta p square z, is a weakly holomorphic modular form of weight 1 on the large congruent subgroup gamma naught of P square intersection gamma 1 of P.
So
I'm going to explain what the adjustment is in a different slide. Yes, please.
yeah, so R sub P you're going to define later.
Yes.
Okay.
Yes. In the very same paper, he also considers the action of the congruent subgroup gamma 1 of P on the elements of the P dissection of the rank generating function. One of the problems that I pursued in my doctoral work was to consider the action of other congruent subgroups of on the rank section element that led me to find a symmetry property between these dissection elements. And subsequently, I also did the extension of this phenomenon to Andrews-Garvan crank of partitions, and both of them I'll be discussing now. Before that, when I say dissection over here, I talk about the dissection elements and the symmetry between those dissection elements. That is my work. So I would like to talk a little bit about what I mean when I say dissections. So here is the rank generating function, and owing to properties of the rank function, when we first learned the rank function, one of the basic properties of rank function that we learn is that, let's say, if nkpn denotes the number of partitions of n with rank congruent to k modulo p, then nkpn is equal to np minus kpn. I'm pretty sure many of you have seen this if you have attended courses in partition theory, courses on which cover these rank type statistics or the partition rank or partition crank. The same also holds for the partition crank. So owing to that property and the properties of these roots of unity, we can write the rank function in terms of these rank differences. So as you can see, R zeta P Q, which is nothing but the two variable rank generating function, is equal to the sum of these rank differences. And one research direction with respect to these P dissections is to find formulas for the generating functions of these rank differences in terms of eta products, generalized eta products, modular forms and functions, and or Lambert series, and the methods of finding or proving these identities involves two kinds of techniques. The first is an adaptation of the method of Atkin and Swinerton-Dyer in the same paper, 1954 paper. And the other one is a modular approach that involves arguments coming from the theory of automorphic forms. If you are looking for some nice reference with regards to finding the generating functions for this kind of work, then there is a series of papers by Jeremy Lovejoy and Robert Osborne written in 2008, 9, and 10, where they do such rank type different, where they find generating functions for these rank differences for rank of over partitions, rank of partitions without repeated odd parts, and I don't remember the last one. It's a series of papers in 2008, 9, and 10. And also the work of Atkin and Swinerton-Dyer, of course. Here's an example. The 5 dissection of the Dyson's rank of partitions given by Ramanujan. It's found in Ramanujan's notebook, in one of Ramanujan's notes, where you can see that these are the rank dissection elements written in terms of products, generalized eta products, or I would rather call them Jacobi products. Of course, some of those elements also have these correction factors attached to it, which I'll again define in a later slide. Some of them are just products. And the fifth one is 0, which corresponds to Dyson's rank conjecture, which is not very difficult to see. The fifth one is for R4, which is 5n plus 4 over here, and the coefficient is 0, which implies the Dyson's rank conjecture, and or so to say the mod 5 Ramanujan congruence, partition congruence of Ramanujan. That takes me to the symmetry phenomenon for the partition rank, the first part of my talk today. To explain, I'd rather give an example first and then show the result. Here is the 7 dissection, also found again in Ramanujan's lost notebook, written equivalently in terms of generalized eta functions. As you can see on the right-hand side, we have these eta products, conf eta products, which are the dissection elements of this rank function. And just like the previous dissection, we had these correction factors attached to some of these elements, dissection elements, we also have the following correction factors attached to 3 of these elements here, which I have taken to the left-hand side, so that the right-hand side only has these products. And doing a little bit of a manipulation here, trying to write it a bit neatly, we get the following. Here are the 7 elements of the dissection. Once again, the first element being 0 corresponds to the mod 7 Dyson's rank conjecture, and the rest of it is here. If we observe closely, we will see that for these dissection elements marked in red, there is some symmetry between them, and there is also some symmetry between these elements marked in blue. So as to say, these subscripts below are being permuted among each other, the ones in red and the ones in blue. The red ones, m equals to 1, 2, and 4, correspond to when minus 24m is a quadratic residue modulo 7, and the blue ones correspond to when minus 24m is a quadratic non-residue modulo 7. And the reason behind this symmetry is through a modular argument that I explained in the slide after this one. Before that, I just want to define the dissection elements explicitly. So we have 2 cases, one when minus 24m is a non-residue modulo p, and when it is a residue modulo p, we have to attach these correction factors here, this correction factor here. To tie this to the examples that we saw before for the 5 and 7 dissection, what happened over there, so these are the dissection elements, which mean that when added, they will give you the rank function, the generating function for the rank, the entire function for the rank. So these elements appeared over here. Let's say if I go back to the 5 dissection, these are the correction factors, which when added, give you this entire factor over here. Those factors over there, correction factors, corresponded to the dissection elements for which this m below was a quadratic residue modulo p. Defining the dissection elements in this fashion, we can show that the symmetric behavior arises from the following theorem. Following the following theorem. This appeared in the Ramanujan journal a couple of years back, where we see that the action of the congruent subgroup gamma naught of P on an element of the dissection lands us in a different element of the dissection, but it preserves the quadratic residue nature. So as to say, if M is a quadratic residue modulo P, so is MA square, and if not, then not. And we have these prefactors out at the front, a ratio of signs and root of unity. Here is an illustration of this. So we consider the M equal to one element of the dissection, the 7 dissection of the partition rank, and the following matrix in gamma naught of 7. As you can see, the determinant is 1, and here is a 7 there. So we are going to look at the transformation of this product under the congruent subgroup gamma naught of 7, considering the following matrix. For that, we know the transformation of these eta, of the eta function very well. For these Biaggioli theta functions, their transformation property under a matrix A in gamma naught of n was given by Biaggioli in his paper itself, and also the following property. Using those, we restating this is the matrix that we are considering, and the action of F. Action of the matrix A on F gives you the following, where we have minus 1 to the power something times some root of unity times F of n rho A. The rho here changed to rho A, where A is the first element of the matrix. And we also need to use the following property. And doing some calculations over here, what we see is we started from K7 1 zeta 7, and it resulted in K7 4 zeta 7 to the power 4. You can see that the 4 here, the zeta, changed to zeta to the power 4, which is the last element of the matrix A. And the 1 here, KPM, M equals 1, changed to MA square. M is 1 and A is 2, so 2 square is 4. So that precisely matches with our symmetry result. Here is another symmetry result that we found between the elements of the dissection, more precisely between the coefficients. here is an identity given by Garvan in his 2019 paper, where this is an identity expressing the K11 zero element of the dissection in terms of generalized eta functions, J11Ks, K from 1 to 5. These are how the generalized eta functions, these are the generalized eta functions that occur in this dissection. And here are the coefficients, which are cyclotomic. So just by looking at them, it does not seem like there is any symmetry between these elements. But if I write them in a neater fashion, here is what I get. So I'm multiplying by ratio of signs and writing them in this pattern. So now we can see some kind of hidden symmetry between these coefficients. What I'd like everyone to observe here is that the second coefficient is obtained from the first one by replacing zeta by zeta square. So if you replace zeta by zeta square here, you get zeta to the power 4. Zeta by zeta square, you get zeta to the power 18, which is zeta to the power 7, and so on. The third one is obtained from the first one by replacing zeta by zeta to the power 3. The fourth one by zeta to the power 4, and the fifth one is obtained by replacing zeta by zeta to the power 5 in the first coefficient. So the following result explains this symmetry. So if this symmetry occurs, provided we can talk about this result, we can find this result, provided we can write the dissection element in terms of these generalized eta functions, or our Biot functions, or our functions J, which are linearly independent over Q. Then, as I said, from the first cyclotomic coefficient, you can generate the rest using this result. Okay, that ends the first portion. And here is the symmetry phenomenon for the partition crank, which is the next project that I pursued. So if MRTN denotes the number of partitions of N with crank congruent to R modulo T, once again, this is the partition crank discovered by Andrews and Garvin, where once again we are letting zeta P to be the primitive pth root of unity, and the generating function is given by C zeta P Q. Then we tie the crank generating function to a class of generalized eta functions which are related to Klein forms, and the transformation of these Klein forms are well known. So that gives us the following result, where if I define by F1C L over PZ to be this, where we have L here in the denominator, then the L changes to DL reduced modulo P, and we have a plus or minus 1, sorry, a root of unity out at front, and this occurs under the action of the congruent subgroup, once again, gamma naught of P, which was the same as the partition rank. Of course, this is the transformation for this particular function. The goal is to tie this function with the crank generating function. And this project is dear to me. This is a project that appeared in the Hardy-Ramanujan journal, of which Atul sir is one of the editors. So we can write the crank generating function in terms of these F1 functions that I have described before, and using the transformation result for the F1 function that we obtained in the previous theorem, we can deduce that the crank generating function times the low eta product here is a weakly holomorphic modular form of weight 1 on the congruent subgroup gamma naught of P square intersection gamma 1 of P. There is no bigger reason behind attaching this eta product here. It just helps with the transformation and makes the modular object of weight 1. This is a weight half, that is weight half, that makes it 1, is why we have attached that there. We also have the following analog of the rank dissection elements for the crank sum. So the dissection elements for the rank involve two cases. one when minus 24m was a quadratic residue and one for when it was a non-residue modulo P, but the corresponding thing for the crank generating function does not involve the quadratic residue case, so it is much easier to handle. So these are the dissection elements that we define, and that leads us to the analogous symmetry result for the partition crank, which is exactly the same as the partition rank. And to find this result is easier than the partition rank. The partition rank, finding the result for the partition rank involves breaking it down into different modular objects and looking at their transformations and transformations one by one. But the crank function is easier to handle because it is a single product. So because it is a quotient, so that is easier to handle. Once again, the congruent subgroup this time for this symmetry result is again gamma naught of P. Back to Dyson's rank conjectures, because I want to explain something more that I did in this paper. Something derivative, but still a nice exposition of some techniques here. So back to Dyson's rank conjectures. Here are the two conjectures given by Dyson in 1944. And the proof of these conjectures, as I said, was found by Atkin and Sunderton Dyer in 1954. And their proof involved identifying the generating function for these rank differences. And to prove the result for 7n plus 5 and 5n plus 4, they simultaneously prove identities for all r from 0 to p minus 1. So for proving the 5n plus 4 conjecture, they had to look at look at identities. They had to find identities, prove them, prove 5 of them from n0 minus n1 to n5. Sorry, n0 minus n1, n0 minus n2 to n0 minus n4, so 5 of them, and 7 of them for the 7n plus 5 conjecture. And what they state in their paper, I think I had this open somewhere, but what they state in their paper is that they are unable to simplify their result to obtain just the 7n plus, just the proof of this one, the 5n plus 4 or the 7n plus 5. To prove that result, they have to look at all of these identities. They have to find the generating functions for all of them using the theory of elliptic functions and some more stuff. Garvan, but in 2019, gave a new proof of this result of the Dyson's rank conjecture using the theory of modular forms by calculating the orders of the 0th element of the dissection at the cusp of the congruent subgroup gamma 1 of P and using the valence formula. So a little bit of a background here that the proof of the crank theorem, or let's call it crank conjecture, which became a theorem later on, proof of the crank conjecture, owes its beginning to the vector crank found by Garvan in 1986 in his thesis. So the vector crank divides the partitions of 5n plus 4, 7n plus 5, and 11n plus 6 into 5, 7, and 11 equinumerous classes. And the proof of the vector crank theorem, which is the following: mod 11 involves an elegant utilization of Jacobi's triple product identity and Winquist identity to show that the coefficient of q to the power 11 plus 6 in the generating function for the vector crank for p equals 11 is 0. And subsequently, Andrews and Garvan show that the ordinary crank and the vector crank are same for n bigger than or equal to 2. What I do in this paper is I try to mimic Garvan's proof, Garvan's new proof using the theory of modular forms to prove the Dyson's rank conjectures. I mimic that proof. So if MRTN denotes the number of partitions of n with crank congruent to R modulo T, then this is the crank conjecture or crank theorem. And in our setup, what we do is we consider the m equal to 0 element of the crank dissection, like Garvan used the m equal to 0 element of the rank dissection. And as stated before, this is what the dissection element looks like, some of these cranks. And the crank theorem is equivalent to showing that this general dissection element for p equals 11 and m equals 0, l equals 1 is equal to 0. This being equal to 0 would mean that this part in brackets has to be 0, which means that these things have to be equal, because if they are equal for each of those residue classes, then that can be factored out. And if that can be factored out, then what will remain is the sum of these roots of unity. And we know that the sum of those 1 plus zeta squared dot up to zeta p to the power p minus 1 or zeta n by n minus 1 is 0. So to prove this statement, we have to resort to the valence formula. So for F, a modular form of weight K with respect to the congruent subgroup gamma of finite index in the special linear group, we have the following: that the order of F at with respect to that congruent subgroup, which is the sum of the orders of F at the cusp of the congruent subgroup, is equal to 1/12 of mu K, where mu is the index of gamma in SL2Z and K is the weight of that modular form. So using this, we give, not using this, no, but we give in the following table, we give the order of the m equal to 0 element of the crank dissection at the cusp of the congruent subgroup. So here are the orders, and hence what we find is what we do to find this is the crank generating function with z replaced by zeta p is related to those Klein forms whose transitions and orders are well known. So using that, we can find the lower bounds of that particular dissection element at the cusps of the congruent subgroup, and adding them, we find that the order of that element with respect to gamma 1 of 11 is bigger than 5. But mu, the index of that congruent subgroup gamma 1 of 11 with respect to SL2Z, is only 5. K is 1. We had the product attached on the left here, which when multiplied with the crank sum makes it of weight 1, makes that element of weight 1, which means mu K is 5, and then the valence formula would imply that the 0th element of the dissection is identically 0, and that proves the crank theorem. That takes me to the last part of my talk, which is on the symmetry phenomenon for the over-partition rank and crank statistics, which is a new work. This is something that I think we have finished for a while, but still we are in the process of writing and submitting it. The writing part is also done, but we have just not submitted it yet. Because we had found some more identities here. One of the works that I have done in these projects that I have defined before, that I've talked about before, is not just the symmetry phenomenon, but we have also tried to find identities, explicit identities expressing those dissection elements in terms of generalized eta products for higher primes. That is what we are doing here as well. But I talk about the symmetry result for the analogous symmetry result for the over-partition rank and crank here. So we know that the over-partition is a generalization of the partition function where the first occurrence of a number may be overlined. Here is an example, and the Dyson's rank of an over-partition is defined exactly the same way as the rank of partitions, Dyson's rank for partitions, the largest part minus the number of parts, without considering whether the part is overlined or not looking at that fact. To that end, let OZQ denote the number of partitions over partitions of n with rank m. So here is the two variable over partition rank generating function. And once again, replacing z by a primitive p-th root of unity, the modularity of this function is due to the work of, we know the modularity of this function first due to the work of Brinkman and Lovejoy in 2007. They show that the over partition rank function minus the model integral of this theta function here, which is the non-holomorphic part, is a weak mass form of weight half on the congruent subgroup given by the following. Years later, Chris Jennings-Schaefer, a student of Frank Garvin, reconsiders the modularity of this function, and bypassing the approach of Brinkman and Lovejoy, he constructs the completion of the over-partition rank function to a harmonic mass form, which is the sum of an easily understood modular form, which is right here. The P function, which I have defined right here, is the nice modular function, and a harmonic mass form due to Zweigers, which is this function n, which is mu tilde, which is found, whose transformation and properties are found. The modularity of this function is found in the work of Zweigers in his thesis. Jennings-Schaefer gives an explicit and compact transformation formulas to determine a larger subgroup of SL2Z on which the completion of the over-partition rank function, which is the following, is a harmonic mass form. This is his result, where the congruent subgroup that he has found is this particular one. And the case C equals P for prime P bigger than 3 is the result of Brinkman and Lovejoy stated in the previous slide. What we do is that with the introduction of a simple multiplier, we narrow down the transformation of all the functions involved in the expression for the over-partition rank function in the work of Jennings-Schaefer. These are the functions that are involved in the generating function for the over-partition rank. To a simpler and larger congruent subgroup gamma naught of 2p squared intersection gamma 1 of p, since the multipliers appearing in the results of Jennings-Schaefer, which I don't explain here. This problem also involves finding the over-partition analog of the adjusted rank function RPZ given by Garvin. So here I talk about the adjusted rank function as promised. So a flashback to the 5 dissection of the rank function due to Ramanujan. So here were the products. I have brought the correction factors to the left and kept the products on the right. And it is not very difficult to see that these products are weakly holomorphic modular forms of weight half on this congruent subgroup gamma naught of 25 intersection gamma 1 of 5, which is a special case of gamma naught of p square intersection gamma 1 of p when p is 5. Garvin, in his paper, gave a generalization of this result of Ramanujan so as to say what he found was the rank generating function minus this particular correction factor, where the phi pa is defined by this Q series, which reminds us of the generating function of the rank, but not really. This function times the Lonita product here is a weakly holomorphic modular form of weight 1 on the general congruent subgroup gamma naught of p square intersection gamma 1 of p. And the p equals 5 case is the one due to Ramanujan on the previous slide, As I said, finding the symmetry result for the over-partition rank involved finding an analog of this result, which I talk about in this block. This factor allows us to complete finding that factor, which will be analogous to this factor over here, or phi p over here, allows us to complete the over-partition rank function to a weakly holomorphic modular form on a larger and nicer congruent subgroup, improving the results of Brinkman and Lovejoy and that of Jennings-Schaefer. So the second target is to define the dissection elements of the over-partition rank function, because we are looking at the symmetry of those dissection elements. Here is what the dissection element for the rank look like. For when minus 24m is a quadratic residue modulo p, we did not have those correction factors, and we do have the correction factors when minus 24m is a non-residue modulo p. So here is what we found in regards to the modularity of the modular structure of the over-partition rank generating function. We see that the over-partition function, where the two variable function where we are replacing z by root of unity, zeta p, minus this correction factor, where this time the phi pk is defined by the following series, times this product this time, it's a different product this time, the quotient of these two eta products times the adjusted over partition rank generating function is a weakly holomorphic modular form of weight 1 on the large congruent subgroup gamma naught of 2p square intersection gamma 1 of p. I give a summary of the proof here, which I don't think I will have time to cover entirely. So instead, what I would like to say here is that what happens over here is to prove that it is weakly holomorphic. If I go back to the breakdown of the over partition rank function due to Jennings-Schafer, we see that the object P here is nice. It's a modular object, nice modular object. But we have the model integral of the theta function here, which is non-holomorphic. It's not very difficult to see that this is a non-holomorphic function because there is a tau bar here, the complex conjugate, so it will not satisfy the Cauchy-Riemann equations. So this is the non-holomorphic part that we have here, and the n function here is nothing but the mu tilde function of Zweger's, which also has a non-holomorphic part. If we go back to Zweger's thesis, we'll see that this also constitutes of a non-holomorphic part and a non-holomorphic part. And those two together, there's a minus here, those two together, somehow they will cancel out, and the non-holomorphic part will get annihilated, and we'll be left out with only holomorphic parts, which is why the adjusted rank generating function that I have defined over here is a weakly holomorphic modular form of weight 1 on this nice and large I loosely explain in this summary of proof. As you can see, subtracting the expressions for these two, the non-holomorphic parts cancel out, and this is what we get, which is weakly holomorphic. This is the same result of ours in a equivalent form. Once again, the object P was nice and modular, but the transformation of that object, for once again, is similar to this function is actually similar to the partition crank that I had explained before, and the transformation of that is not very difficult to find because it is related to Klein forms. And for the transformation of n, which involve mu tilde, we have to resort to Zweger's results. The proof is overly technical, which is why I'm not including it here, but that brings me to the symmetry result, analogous symmetry result for the over partition rank, where we have the following analogous definition for the dissection elements of the over partition rank function. We have two cases once again. When minus m is a quadratic non-residue modulo p, we do not have the correction factors, and we do have them when minus m is a quadratic residue modulo p. And here is the symmetry result for the over partition rank, where we see that the action of the congruent subgroup gamma naught of 2p this time on a element of the dissection glances in a different element of the dissection, once again preserving this quadratic residue nature in the same way. And we have the following roots of unity out at front. Here is the analogous symmetry result for the first residual crank of over partitions, which is the most natural crank that you can find. This was defined by Lovejoy, Osborne, and Brinkman in a paper somewhere around 2010. Here is a summary of the proof. Once again, I'm not going to go into that, but here is a summary of the modularity results that we have found. The partition rank and crank, attaching the multiplier eta p square z makes the entire thing of weight 1. The difference is the statistic difference of weight half. This is weight half, that makes it weight 1. Those two are congruence, are weakly holomorphic under the following congruence subgroup. And similarly, we have to attach the following multiplier to the over partition rank and crank to render them weakly holomorphic modular forms of weight 1 on this nice and large congruence subgroup. And their proofs, in summary, to summarize, their proofs employ transformation results for theta functions, their model integrals, client forms, and Zwieger's functions like mu tilde. Like I said before, I think, how much time do I have?
Maybe 5 to 10 minutes. Yeah.
Okay. I'll try to summarize in 5. I just want to explain a little bit more about explicit dissections for over partition rank and crank modulo 11 using an automorphic algorithmic approach in Penn and Sage. One of the works that we have done in these papers of ours is not just to find these symmetry results, but we also try to find explicit identities for these over partition rank and crank functions, or partition rank and crank and over partition rank and crank functions in terms of nice modular objects. The 3 papers of Lovejoy and Osborne from 2008, 9, and 10 that I had described were one of the first papers, I believe, that did this thing, not using a modular approach. Of course, they used the techniques of Atkin and Swinnerton Dyer. Like I said in a slide before, here is the identity for K11, 0, the 11th element of the 0th element of the 11 dissection of the rank generating function due to Garvan in his paper, where you can see the things on the right hand side are quotients of generalized eta products, and of course the quotient of eta products and generalized eta products. So what we do is we try to do the same for not just 11, 0, the 0th element of the dissection, but all elements of the dissection. And the beauty of the symmetry result is that if we can find the identity for one of them, one quadratic residue case, one quadratic non-residue case, and the 0th element, then we can find for all of them because of the symmetry result. And we have done that not just for p equals 11, but also for p equals 13, 17, and 19 in the partition rank and crank case, but for over partition rank and crank, we stop at 11 because the calculations in Maple get too hard. So I try to give a demonstration of what we have done. Of course, this is very minimal. It's very minimalistic what I have done here. This would take a long time to explain, I would say, because it involves a lot of experimentation in Maple. So what we are doing here is we are trying to find a nice basis, a suitable Jacobi product basis for gamma 1 of 22 to express the crank differences in terms of generalized eta products. So we are considering the space of cusp forms of on gamma 1 of 22 of weight 3, and we are trying to create a Jacobi product basis out of it. The worry here is that we pull this from Sage onto Maple and try to express the crank dissection elements in terms of these basis elements. But the thing is, what we want is a nice basis that has products, the elements of the basis being products and not just series. So that's what we want. So we do some experimentation and we find that this is not going to work. This space of cusp forms on gamma 1 of 22 with weight 3, that is dimension 20, this is not going to work. That's what we find. Moving on, we look at this space now. The modular forms on gamma 1 of 22 with weight 4 is what we look at next, and we try to find a suitable Jacobi product basis here. And through some experimentation, we are able to convert the elements of this basis into a new basis whose elements are actually products. So now the problem is Sage gives us the elements that are holomorphic. The basis elements that Sage gives us are holomorphic, but the crank differences do contain some poles. So what we need to do over here is we need to find a eta product or quotient of an eta quotient which will get rid of those poles. So through some experimentation, this is the eta quotient that we find that lifts our crack differences to weight 4, and it also gets rid of the poles. Now, this, as you can see, is of weight 3. So our crank differences, as you can see, no. Yes. So what we do is we multiply this with our crank differences to get a weight 4 object, and the elements from the basis that we were considering are that the basis that we were considering is the basis for the space of modular forms on gamma 1 of 22 with weight 4. So now we can express our crack difference times that particular eta quotient in terms of our basis elements, and this is what we get. This is not a refined example. Through some more calculations, we are able to obtain integer coefficients instead of rational numbers over here. But of course, once again, this involves a lot of experimentation in Maple. I owe this to the Maple package of Professor Garvin. One of the functions there is the find lean combo that lets us express these elements. We convert the crank sum times the eta product into a series, and this find lean combo helps us express this first input, in terms of the basis elements that lie in this particular set, and we get the following identity. And of course, we refine this identity later to get a nicer one. Okay. A third installment in this symmetry phenomenon is in the works, which is on the modular symmetry of the M2 rank of over partitions. These were first defined and studied combinatorially by Morrill, and Jennings-Schaefer and Holly Swisher established that this MD rank is the holomorphic part of a certain harmonic mass form of weight half. This is a paper of theirs that appeared in JMA. And I think the D equals to 2 case corresponds to the over partition M2 rank, and D equals to 1 case corresponds to the Dyson rank, which we have already found. So actually doing the if we are able to find a symmetry result for this MD rank, it will bypass it will supersede the work we have done for rank of over partitions. But the generating functions here are much tougher to handle and would require some more work, I believe, and this is a work in progress. That concludes my talk. Here is a series of, here are the references that we have used. The thesis of Sanders Zegers that started it all, and the paper of Brinkman and Ono, where they first described the modular structure of the partition rank that appeared in the annals. The subsequent paper of Brinkman and Lovejoy, which did the same thing for the over partition rank, and our papers. Thank you.
Thanks, Rishabh, for a nice talk. Any questions?
So I have one or two questions. Thank you, Rishabh, for a wonderful talk. So first, you started with we have seen that Ramanujan's 3 famous congruences, and from there, Dyson gave concept of rank, and which was explaining first 2 congruences, and then crank came, right? So now Ramanujan gave more congruences like modulo 25 as well as modulo 49, and the higher power, more generally, like 5 to the power A, 7 to the power B, or 11 to the power C. So as far I know that rank for those congruences also has been studied. Okay. So now my question is that whether someone has like, let's say modulo 25. Okay. So there is some rank statistics which explains the modulo 25 congruences. Now, whether the rank generating function corresponding to that rank statistics, whether rank generating function has been studied, can you say?
No, I
The
don't think I know about this.
modularity of that rank, because modulo 25, if there is a rank statistics, so I can
Uh-huh.
consider the rank generating function again, and one can
Uh-huh.
study the modularity of that rank generating function.
I think the foundational work of that is by Garvan, Kim, and Stanton
Okay.
in Inventions. So,
Okay.
but that gives the rank statistic. I don't know the modularity thing whether anybody has studied.
Okay. Yeah.
No, I don't know about it either.
Because that's also natural question, like as we are studying corresponding to this Dyson rank, that the rank generating function and modularity of the rank generating function. And one more thing, like RZQ, let's say that is the rank generating function. Then they have Brinkman Ono, I think, studied when Z is zeta p, right?
Yes.
The modularity of that. Now, my question is that instead of zeta p, if we consider, let's say p, not p prime, but p is some composite number, let's say 5 into 7, and we
Mhm.
consider the pth primitive 35th root of unity.
Okay.
I'm considering some a composite number and primitive that eighth root of unity or nth root of unity. So in that case, do you know the modularity of that object?
I I don't want to give wrong information, but I do believe that they do consider stuff like this actually. The thing
Okay.
that I have shown here, because let me show you why I believe that. But once again, we need to check their paper to be sure. But
Okay.
um,
Yeah.
look
So
at this result. I'll show you one result here. Uh, right, I think this is the result that I'm talking about.
okay.
Um, I I have a feeling that this work that they have done is
Okay.
not just for a prime.
Mhm. Yeah, many a times, like I have also seen like
Yeah,
zeta p, but like I have not seen like some composite numbers, primitive root of some composite number, and in just replacing z by primitive root of some composite number. That is my question. Then do you have? It may have maybe the modularity property may get disturbed by once we consider. I don't know. Like just I was, yeah. Okay.
it's just that first thing is that I have seen, I can tell you two things here. First thing is that I have seen results here where you see they use something of the sort that instead of zeta p, they consider zeta c, where c
Okay.
is co-prime, where c is co-prime to some other number like some other number,
Okay.
you know what I
Okay.
mean, right?
Okay.
GCD
Okay.
of c comma something
Mm-hmm.
is equal to 1. I have seen
Mm-hmm.
stuff like that, one
Okay.
thing.
Okay.
The other thing is, if I go back to my result with Professor Garland, this kind of a result, right? Where is it? This one, right?
Okay.
So it is not necessary to consider, I mean, the congruent subgroup has to be 2p, but it is not necessary to consider 2p here.
Okay.
You understand what I'm saying? So it is not necessary to consider 2p here through a coset argument because these are normal subgroups, right?
Mm-hmm.
So you can actually consider this to be a C here,
Mm-hmm.
and still, when you do the action here, then you can write that matrix A in terms of two things on the left-hand side and right-hand side, something times something and something inverse. And using that coset thing, the normal thing, the normal subgroup thing, you can actually find the transformation for a general, putting a general C here as well.
Okay.
So I believe that something is there in that regard.
Okay.
It's actually, I should have been able to answer your better
No, it's okay.
answer,
Yeah.
give your answer better, but I actually don't remember the paper
Yeah.
entirely.
I was just
But I do
curious to
believe that,
know whether that kind of result has been studied or not. Okay.
right. I do think that I have seen something of that sort, that the result that they have is for a general C, where C is co-prime to something. I think I've seen something like that.
Okay. So
But I
one
can
more
look at it
thing.
better and give you the
Yeah,
correct
one
answer.
more
Yeah.
thing that Andrew's SPT function also does have like satisfy this three congruences, but there
Yes.
are like for first two congruents there are some statistics, and does someone has also studied like the rank generating function modularity of that also like the way you have studied?
They have definitely studied the modular structure of the SPT function. That is true. People have done work on that. That is a done deal, I guess. But there are works of the Ono group itself that have studied the modular structure of the SPT function. But I don't know if the SPT. I
So
can tell you one
SPT,
thing. They
like SPT rank or SPT crank, whatever statistics might be, and then the generating function SPT rank generating function or SPT crank generating function, let's say. Then I want to know that whether a modular property has been studied or not. Okay. So
they have.
okay.
But the symmetry property that I have studied, no one has studied that,
Mhm.
because
Okay.
even the five dissection of the SPT function is not known yet. We
Okay.
don't know the five dissection of the SPT function as well. So
Okay. I see.
um, uh, even I don't think I can think of anything
Adul
here.
sir wants to say something. Yeah.
Yes, please.
Yeah, I had one question. You had said about the rank dissection function that you found, like R1, R0, R1, R2, R4, and similarly you did it for not just 5, 7, 11, but also 13, right? And which others? Which other primes? 13 and
13, 17, 19 for
oh.
the
So for
partition
13,
rank.
did
But
you
the thing
use
is,
the
what we have,
yeah.
I'm sorry.
Yeah, for
No,
13, did
what
you
I
use the work of O'Brien?
um we took some idea, yes. But the thing is, we did take some idea there, but that was initial work. After a while, what happened was, this is actually a little bit something that should have been we should have reported, I guess, or published, I guess. But this was a very good experimental work that ended up in us finding a program that will generate such um, identities. So what we do is we take the rank function, the dissection element of the rank function on the left, and on the right we have these linear combination of these generalized eta products with cyclotomic coefficients, right? So that is what we did. That is the part that I'm talking about. Like if you go back, if I show this work of Garvan, yes, this is the work of Garvan, right? In 2019 paper, this is the only identity, or there's one more identity that Garvan has in his 2019 paper. So this is exactly what we did for P equals 13, 17, 19, and K equals 0 to, this is the one for K equals 0 here. But we have done this for K equals 1 to all of them. So what happened after a while is we did use, yes, we did take idea from O'Brien's thesis to find the one for 13 at the beginning. 13.0, Garvan has it in his paper, but we did try using his paper to find the others. But after a while, we ended up finding a program where you can do this for anything, for any number.
Oh, so my question is, are the results for 5, 7, and 11 somewhat better in terms of simplicity or elegance
Yes.
as compared to the other higher primes?
Yes, obviously, yes.
I mean, not just at the ones like R4 equal to 0, even at the other values of R sub I for the higher
Yes, if you
are,
look at this one, K7, right? So
yeah.
if you look at these identities for K7, these are the dissection elements for 1 to 6, right? So all of them are just one product if you look at the right.
Yeah.
But If I now go to 11, then you can see that just one of them is a sum of 5 products. This is just one of it. So the others are also sum of 5 products. So it gets tougher and tougher as you go on. For 19, we need even more. For I think 19, we have 54 functions, I believe.
Okay,
So, yes.
great. Any other questions? If not, let's thank Rishabh for a nice talk.
Yeah.
Thank you.